Welcome back. In this lecture video, we're going to start talking about two topics that you would have been exposed to at least a little bit in your first methods class, power and precision. Now, these are two topics that are very important from an experimental design standpoint because when you do design an experiment, part of what you're trying to do is to design the experiment in such a way that you maximize the power of hypothesis tests and the precision of estimators based on the amount of experimental material and other resources that you are investing in an experiment. Now, to do this, we're going to first look at the context of the one sample z-test. And once we talk about these concepts in that context, then we will expand it as we go throughout the course. So let x1, x2, and so forth up to x sub n be a random sample of size n from a normal distribution with mean mu and variance sigma squared. Let x bar denote the sample mean. Now recall that the standardized random variable, the standardized version of x bar minus mu over the standard error of x bar, which is sigma over the square root of the sample size. And remember, sigma is the standard deviation of the population. So this standardized version of x bar, which we're denoting by z here, has a standard normal distribution. As long as the population or distribution that we're sampling from is normal, then the standardized version of x bar will be exactly normally distributed as well. Now, if the underlying population that we're sampling from is not exactly normal, then at least if we have sufficiently large samples, then by the central limit theorem, the standardized version of x bar will be approximately normal. So we'll at least have approximate normality, and we'll have exact normality of the standardized version of x bar if we actually are sampling from a normal distribution. Now, the fact that this standardized version of x bar has a standard normal distribution provides the basis for inference procedures for the population mean mu when sigma squared, the population variance, is known. Now, let's focus on hypothesis tests for now. The hypotheses that can be tested about mu are given on the following slide. And so these are hypotheses that we would have looked at in a previous lecture. So again, we have our three types of hypotheses. Hypothesis A is a two-tailed test. All right, the null hypothesis says that mu is equal to some hypothesized value mu sub 0 versus the alternative hypothesis, which says that the population mean is not equal to that hypothesized value. Hypothesis set B is a left-tailed test. The null hypothesis says that mu is greater than or equal to mu 0 versus the alternative hypothesis, which says that mu is less than mu sub 0. And then finally, hypothesis C is a right-tailed test. The null hypothesis says that mu is less than or equal to the specified value mu sub 0 against the alternative hypothesis that says that mu is greater than mu sub 0. Now, when the population variance is known, or equivalently, when the population standard deviation is known, then we can calculate this version of a test statistic, which has the actual standard error of x bar in the denominator. And you'll recall that we call this z-test test statistic z-calc. All right, so z-calc, the test statistic for the z-test, is the sample mean, x bar, minus the hypothesized value of the population mean, and then we divide that difference by the true standard error of x bar, which is, again, sigma over the square root of the sample size. Now, in order to use this test statistic to test hypotheses about mu, we have to understand how it behaves, and that behavior is contained in its sampling distribution. Regardless of whether the null hypothesis is true or not, if we are sampling from a normal distribution, then z-calc will also be normally distributed. And in particular, because we're standardizing by dividing by the standard error of x bar, in either case, we see here that the standard deviation of the sampling distribution of z-calc will be 1. Now, the difference is in their means, and the difference being whether or not the null hypothesis is true. And so if the null hypothesis is true, then the mean of the sampling distribution of z-calc will be equal to 0. And so under the null hypothesis, z-calc will be standard normal. On the other hand, if the alternative hypothesis is true, then z-calc will still be normally distributed with a standard deviation of 1, but the mean of that distribution will be something that is different than 0. And in particular, the mean of its sampling distribution will be equal to the difference between the true value of mu, whatever it happens to be, and mu sub 0, the hypothesized value, divided by the standard error of x bar, which is sigma over the square root of the sample size. And so if the null hypothesis is true, then the sampling distribution of z-calc will be centered at 0. If the alternative hypothesis is true, then the sampling distribution of z-calc will be centered at this particular value. We might think of that as a non-centrality value or non-centrality parameter. All right, so the rejection criteria depend on the type of test, obviously. And so if we have a two-tailed test, hypothesis A, then we're going to reject the null hypothesis if z-calc is either less than negative z sub alpha over 2, or if z-calc is greater than positive z sub alpha over 2. If we are performing a left-tailed test, then we're going to reject the null hypothesis if z-calc is less than negative z sub alpha. And if we have a right-tailed test, then we will reject the null hypothesis if z-calc is greater than positive z sub alpha. So those are the specifics about how the z-test is performed. We have our hypotheses. We specify a hypothesis. We have the formula for the test statistic. And then based on the hypothesis that we've specified, that determines the appropriate rejection criteria. Now, what we want to do is to now consider some characteristics of the z-test, some performance characteristics actually. And those two performance characteristics are the power function and the operating characteristic function. So recall the following characteristics of a test. Power is the probability of rejecting the null hypothesis. In particular, it's the conditional probability of rejecting the null hypothesis when in fact the null hypothesis is false and should be rejected. In fact, I should be a little more careful how I specify this, and so I think I'm going to go ahead and change that bullet point to reflect that. Okay, so I've updated that. I like the way that reads better. So power is the probability of rejecting the null hypothesis when the null hypothesis is false and should be rejected. Now, beta, on the other hand, is the probability of committing a type 2 error. In other words, it's the probability of failing to reject a false null hypothesis that should be rejected. Now, the relationship between power and beta is that power plus beta is equal to 1. Now, that can also be written power equals 1 minus beta, or equivalently, beta is equal to 1 minus power. But either way, the relationship is that power plus beta is equal to 1. Now, we're going to investigate these test characteristics in more detail. Power and beta are not fixed constants. Power is a function of several quantities. In particular, power depends on the true value of the population mean. All right, and with that in mind, we're going to denote the power function evaluated at mu, the true value of the population mean, using this notation here, lowercase Greek letter pi, and then using function notation, the parentheses, right? So we have the argument there in the parentheses. So the power of the test evaluated at mu is denoted by this notation here. Now, the probability of a type 2 error, because power is a function of mu, the probability of a type 2 error is also a function of mu. And so to reflect that, we'll denote the probability of a type 2 error as a function of mu this way. So beta of mu. Now we can graph each of these functions, the power function evaluated as a function of mu and the beta function as a function of mu, versus or against mu to get a sense of the performance of the test. Now the graph of beta versus mu is called the operating characteristic curve, and the graph of the power function versus mu is just called the power function graph. Now the functions pi of mu and beta of mu depend on the form of the alternative hypothesis. So let's look at expressions for these functions. And so remember the three types of hypotheses that we can test are the two-tailed test, the left-tailed test, and the right-tailed test. Now, one question I might ask you is that for each of these three tests above, what would the power function of an ideal test look like? Okay, so let's first consider the two-tailed test. Okay, so remember that power is the probability of rejecting the null hypothesis when the null hypothesis is false. Now, for a two-tailed test, where the null hypothesis is that the mean of the population is equal to some specified value, which we're denoting by mu sub 0, and mu sub 0 is located right here on the horizontal axis here. So the horizontal axis is the parameter space for the population mean. The population mean can be any real number. And so this is the location right here of mu sub 0. And the null hypothesis says that mu is equal to mu sub 0. And so if the null hypothesis is true, then mu is equal to mu sub 0. So this is the single location here on the horizontal axis where the null hypothesis is true. And if the null hypothesis is true, then obviously we do not want to reject it. And so the ideal test would never reject a true null hypothesis. And so the corresponding probability of rejecting that true null hypothesis would be 0. All right, and so that is why the probability of rejecting the null hypothesis is 0 right here when mu is equal to mu sub 0. Now, if mu is any other value of mu sub 0, in other words, if mu is not equal to mu sub 0, then the alternative hypothesis is true. Now, that can be the case when mu is either strictly to the left of mu sub 0, or if mu is strictly to the right of mu sub 0. So I'm using the notation here, HO, with this arrow to indicate that this is where the null hypothesis is true, and I'm using H1 over here over this subinterval, and H1 over this interval to identify the alternative hypothesis parameter space, if you want to call it that. So those are the values of mu where the null hypothesis is not true. Now, if the null hypothesis is not true, we want to reject the null hypothesis, and the ideal test would always reject the null hypothesis if it's not true. And so what that means is that if mu is any other value of mu sub 0, the ideal test would have a probability of 1 of rejecting that null hypothesis. And so this is what the power function for the ideal test for this two-sided test would look like. All right. Now, in the real world, we'll never have access to an ideal test. if we had enough information to have an ideal test, then we wouldn't need to test at all, right? And so because we're in a situation where we don't have complete information about mu, about the population, there's no way of constructing an ideal test. All right, but this is at least a goal or an ideal that we can use to compare realistic tests to. Now, if we are performing a left-tailed test where the goal is to try to show that mu is less than some value mu sub 0, if in fact that's the case, the null hypothesis would be that mu is greater than or equal to mu sub 0. And so mu sub 0 is again located right here. And if mu is at or to the right of mu sub 0, then that is where the null hypothesis is true. On the other hand, if mu is less than mu sub 0, if it's out here to the left, then the alternative hypothesis is true. Now, the ideal test will never reject a true null hypothesis, and it will always reject a false null hypothesis. And so the power function for an ideal left-tailed test would look like this. It would be 0 for values of mu that are greater than or equal to mu sub 0, and it would be 1 for any value of mu that is less than mu sub 0. And then finally, the power function for an ideal test of a right-tailed test. All right, and so in a right-tailed test, the null hypothesis says that mu is less than or equal to the specified value mu sub 0, and the alternative hypothesis says that mu is greater than mu sub 0. Now, the values of mu that are consistent with the null hypothesis are values of mu that are at or to the left of mu sub 0, this point right here. Values of mu for which the alternative hypothesis is true are values of mu to the right of mu sub 0. And again, the power function of an ideal test, or let me put it this way, the ideal test would never reject a true null hypothesis, and it would always reject a false null hypothesis. And so the power function for an ideal test would be 0 if mu is at or to the left of mu sub 0, and the power function would be 1 if mu is to the right of mu sub 0. So this is what the power function of an ideal right-tailed test would look like. But again, in the real world, we will never have available to us an ideal test, whether it's a two-tailed test, a left-tailed test, or a right-tailed test. But at least we can use these as goals or ideals that we can use for comparison purposes to the actual tests that we do have. Now let's talk about the operating characteristic function. In the following formulas, beta of mu denotes the probability of committing a type 2 error as a function of the true value of the population mean mu. Now for a two-tailed test, the probability of committing a type 2 error is equal to the probability that our test statistic z-calc is between negative z sub alpha over 2 and positive z sub alpha over 2. Remember that a type 2 error is when we fail to reject a null hypothesis when that null hypothesis is false and should be rejected. Now, we reject if z-calc is either less than negative z sub alpha over 2 or if it's greater than positive z sub alpha over 2. And so we would fail to reject the null hypothesis if z-calc is between those two values. And so for a given value of mu for which the alternative hypothesis is not true, the probability of a type 2 error, in other words, the operating characteristic function for the test, is given by the probability that we do not reject, and that is given by the probability that z-calc is between negative z sub alpha over 2 and positive z sub alpha over 2. Now, for a left-tailed test, we're going to reject for small values of our test statistic. In particular, if zcalc is less than negative z sub alpha. So we would fail to reject the null hypothesis if zcalc is greater than or equal to negative z sub alpha. And so for a given value of mu, for which the alternative hypothesis is true, and so therefore the null hypothesis is false, the probability of a type 2 error as a function of mu is equal to the probability that zcalc is greater than or equal to negative z sub alpha. And then finally, for a right-tailed test, you'll recall that we're going to reject it for large values of our test statistic. In particular, if zcalc is greater than positive z sub alpha. And so we would fail to reject the null hypothesis if zcalc is less than or equal to z sub alpha. And so if mu is such that the alternative hypothesis is true, the null hypothesis is false, then the probability of committing a type 2 error would be given by the probability that zcalc, the test statistic, is not in the rejection region. In particular, if zcalc is less than or equal to positive z sub alpha. So these are the functions, the expressions stated in probabilistic terms, in probabilistic notation, for the operating characteristic function, which again depends on the form of the test, whether it's a two-tailed test, a left-tailed test, or a right-tailed test. And these expressions are stated in terms of the test statistic zcalc. Now, I would just point out that these are in fact functions of mu, but you really can't see that, and the reason is mu is embedded in the calculation of zcalc. You'll remember the formula for zcalc was x bar. Well, we'll look at that in a minute, but yeah, it's embedded in there. In particular, the value mu is part of the mean of the sampling distribution of zcalc. You'll remember that mean value was mu minus mu naught over sigma over the square root of the sample size. Now, in the following formulas, pi sub mu denotes the power function of the test as a function of the true value of the population mean, mu. Now remember that the power of a test is equal to 1 minus beta, 1 minus the probability of a type 2 error. So we could also obtain the power of a test if we had already calculated beta, and vice versa. If we happen to calculate power first, then we could also calculate beta by subtracting power from 1. Now, for a two-tailed test, the probability of rejecting the null hypothesis when the null hypothesis is false, right? So if mu is a value such that the null hypothesis is false and the alternative hypothesis is true, all right, then the power at that value of mu is given by the sum of the probability that zcalc, our test statistic, is less than negative z sub alpha over 2, and the probability that zcalc is greater than positive z sub alpha 2. All right, for a left-tailed test, the power of the test as a function of mu is equal to the probability that zcalc is less than negative z sub alpha. And for a right-tailed test, the probability of rejecting the null hypothesis, the power of the test, if mu happens to be a value for which the null hypothesis is false and the alternative hypothesis is true, then the power of the test for that value of mu is equal to the probability that zcalc is greater than positive z sub alpha. So in each of these two slides, we are expressing the operating characteristic function, the beta function, as a function of mu and in terms of zcalc. All right? So we have the operating characteristic function, beta of mu, and the power function, pi of mu. Now, the operating characteristic function can also be expressed in terms of a standard normal random variable z as follows. All right, and so for the two-tailed test, the beta function evaluated at mu, the probability of committing a type 2 error as a function of mu, would be equal to the probability that z, which is a standard normal random variable, is between these values. All right, and so you can see those expressions that are given here. Negative z sub alpha over 2 minus mu minus mu naught all over sigma over the square root of the sample size. That's the lower endpoint here. The upper endpoint being z sub alpha over 2 minus mu naught over sigma over the square root of the sample size. Now, one nice thing about this representation is that the dependence of the operating characteristic function beta on mu is very apparent. It shows up in both the lower and the upper endpoints. For a left-tailed test, the operating characteristic function as a function of mu is given by the probability that a standard normal random variable z is greater than or equal to negative z sub alpha minus mu naught over sigma over the square root of the sample size. And then for the right-tailed test, the operating characteristic function beta as a function of mu, the true value of the population mean, is given by the probability that a standard normal random variable z is less than or equal to positive z sub alpha minus mu naught over sigma over the square root of the sample size. Now again, the nice thing about these three representations, compared to the representations that involve z-calc, the test statistic, is that the dependence of these probabilities on the true value of mu is very apparent. And in fact, not only can we see that the operating characteristic function depends on mu, but we can also see that it depends on the significance level of the test, alpha, as well as the hypothesized value of mu naught, the standard deviation of the underlying population, sigma, and the sample size. So in actuality, the operating characteristic function is a function of more than just the population mean mu. It certainly depends on mu, but it's also dependent upon the significance level of the test, the hypothesized value of the population mean, the population standard deviation, and the sample size. So the operating characteristic function is really a function of those various quantities, all right? But usually for a given situation, the significance level is fixed, the hypothesized value of the mean is fixed, the standard deviation of the population is at a particular level that has been determined, and the sample size is fixed as well. And so once those quantities are fixed, then the only other quantity that varies or can vary is the value of the population mean, mu, and so that's why we would typically just describe this as a function of mu, but technically it is a function of all 5 of those parameters. Now, graphs of several operating characteristic functions for each of these 3 kinds of tests are shown on the following slides. And so here we have the operating characteristic curve, in fact several curves, for a two-tailed z-test of a population mean. And so this is, again, for a two-tailed z-test of a population mean. And the point here on the horizontal axis where we have this vertical line going through it, that's the position or the location of the hypothesized value mu sub 0. All right, the horizontal axis consists of the, or represents the parameter space for mu, and so all possible values of mu, the population mean. The vertical axis gives us the probability of a type 2 error, or beta, and this graph gives us the possible values, or it gives us the function of beta as a function of mu. All right, and so this is the operating characteristic curve for this two-tailed z-test. Now we have 1, 2, 3, 4, 5 curves, and those 5 curves correspond to 5 different sample sizes. You can see here the black line, black curve, is for a sample size of 9. Then we have it may be hard to tell, but it's a purple curve. All right, and so that corresponds, that's the operating characteristic curve for a sample size of 25. The green curve corresponds to using a sample size of 36. Let's see here. I guess the n equal to 25 curve was blue. The n equal to 64 curve is purple, and then the red curve corresponds to a sample size of 100. And so you can immediately see several things. Let's take any one of these curves. You can see here that for values of mu that are very close to mu sub 0, all right, so again, this is the location of mu sub 0. If mu happens to be close to mu sub 0, then there is a very high probability, a very high likelihood of committing a type 2 error. In fact, as mu gets closer and closer to mu sub 0, regardless of the sample size that we're using, the probability of committing a type 2 error gets closer and closer to 0.95. Now, it's getting closer and closer to 0.95 because the significance level that I'm using here is 0.05 or 5%. So again, the closer that the true value of the population mean gets to mu sub 0, the probability of failing to reject that false null hypothesis, in other words, the probability of committing a type 2 error, gets larger and larger and gets closer and closer to 0.95. Now, as the true value of mu gets further and further away from mu sub 0, then we can see that the probability of committing a type 2 error decreases, all right? And you can see here that as the sample size gets larger and larger, that rate of decrease gets faster and faster for smaller and smaller differences or distances from mu to mu naught. Now let's consider the effect of sample size, and let's consider a particular value of mu. And so I'm going to use my cursor here. Let's suppose that we have a value of mu about right here. And so you can see that if we only have 9 observations, then the probability of committing a type 2 error is very, very high. But if we increase the sample size to 25 observations, then the probability of committing a type 2 error decreases. If we increase the sample size further to 36 observations, then the probability of a type 2 error decreases further. And you can continue on. You can see that as the sample size increases, for a given value of mu that is different than mu naught, as you increase the sample size, the probability of committing a type 2 error decreases. And that should make sense. As we obtain larger and larger sample sizes, we're getting more and more information about the population that we're sampling from, and in particular, more and more information about the population mean. And so we should have more and more power for the test, and therefore there would be less of a chance of failing to reject that false null hypothesis. All right, the next slide contains operating characteristic curves for a left-tailed z-test of a population mean. And again, we have 1, 2, 3, 4, 5 operating characteristic curves corresponding to 5 different sample sizes, n equal to 9, n equal to 25, n equal to 36, n equal to 64, and n equal to 100. And you can see that if the value of mu is very close to the boundary of the null hypothesis space, which is mu sub 0, right? So remember, this is a left-tailed test. And so the null hypothesis is true if mu is here at mu naught or to the right. All right, that's the interval for values of mu over which we do not want to reject the null hypothesis. But if mu happens to be to the left of mu naught, over here, then we do want to reject the null hypothesis. Now, if mu is to the left of mu sub 0, but very close to it, we see that we have a very high probability of failing to reject the null hypothesis, a very high probability of committing a type 2 error. All right, as the value of mu, or 4 values of mu, that are further and further away from that boundary, we see that the probability of a type 2 error drops off, and drops off pretty quickly, at least initially, and then eventually, it gets so low that it levels out. We also see that for a given value of mu, say right here, there may be a large probability of committing a type 2 error if we're only using 9 observations, but if we're using 25 or 36, 64, or 100 observations, all right, the probability of committing a type 2 error is quite a bit less. So we see the impact of increasing the sample size on the probability of a type 2 error. And then finally, we have operating characteristic curves for a right-tailed z-test of a population mean. And so for a right-tailed test, the null hypothesis says that mu is less than or equal to mu sub 0. And so this is, again, the position of mu sub 0. And then if mu is at that point or to the left, then the null hypothesis is true. On the other hand, if mu is to the right of that point, the alternative hypothesis is true, and in that situation we would want to reject the null hypothesis. Now, if the value of mu happens to be to the right of mu naught, but not too far to the right, then again we see that there is a very large probability, a very high likelihood that we will commit a type 2 error. But for values of mu that are further and further away from the boundary of that null hypothesis space, we see that the test is better able to determine that the null hypothesis is not true, and therefore the probability of a type 2 error decreases very quickly. And finally, for a given value of mu, say right here, we see that as we increase the sample size, all right, the probability of a type 2 error decreases. Now, the power function can also be expressed in terms of a standard normal random variable z instead of zcalc in the following way. So for the two-sided test, the power of the test at particular value of mu is equal to the probability that a standard normal random variable z is less than negative z sub alpha minus mu naught over the standard error of x bar, which is sigma over the square root of the sample size, plus the probability that the random variable z, standard normal random variable z is greater than positive z sub alpha over 2 minus mu naught over sigma over the square root of the sample size. For a left-tailed test, the power as a function of mu is given by the probability that a standard normal random variable z is less than negative z sub alpha minus mu naught over the standard error of x bar, sigma over the square root of the sample size. And then finally, the power of the test for a right-tailed test as a function of mu is equal to the probability that a standard normal random variable z is greater than z sub alpha minus mu naught over sigma divided by the square root of the sample size. And so again, the nice thing about these representations for the power functions for the three types of tests is that the dependence of these power functions on mu is explicit. We can see exactly how these quantities, how these expressions depend on mu. And the other thing, like it was for the operating characteristic function, we can also see that power is not just a function of mu, but it's a function of several other quantities, in particular the significance level used for the test, the hypothesized value of mu, the population standard deviation, and the sample size. And so there are actually 5 quantities that the power depends on. But if those other 4 quantities are fixed, as they would be in a given situation, then the remaining quantity that the power depends on is mu. Now, the next several slides show graphs of power functions for the 3 kinds of hypothesis tests. And so let's take a look at what those look like. So on this slide, we have power curves, power functions for a two-tailed z-test of a population mean. And we have 5 curves corresponding to the 5 sample sizes that we're considering. N equal to 9, N equal to 25, N equal to 36, N equal to 64, and N equal to 100. Now notice that all of these power curves have a minimum equal to 0.05 when mu is equal to mu sub 0. All right, again, this vertical line is going through the point where mu is equal to mu sub 0. And the reason that these curves all go through the point mu 0 and 0.05 is because I'm using an alpha, a significance level of 0.05 for each of these tests. So the probability of rejecting the null hypothesis when the null hypothesis is true is 0.05. That's the significance level of the test. Remember that that is the probability of a type 1 error, right? So if mu is equal to mu sub 0, the null hypothesis is true. We don't want to reject it, but there's always the possibility of rejecting it. And that probability is 0.05. And so that's why those 5 curves go through that particular point. Now, if mu is any other value besides mu naught, then the alternative hypothesis is true. And so we would want to reject the null hypothesis. And what these curves give us is the probability of that happening. Now, we can see here that if mu is different than mu naught, for example, maybe it's a little bit to the right of mu naught, but it's not too far away, then we can see that the probability of rejecting is quite small, probably less than 0.1, probably less than 10%. For values of mu that are further away from mu naught, either to the right or to the left, we see that the probability of rejecting the null hypothesis, which again is given or is equal to the power of the test, we see that those probabilities increase, right? The further mu is from mu naught, the greater the chance of rejecting the null hypothesis. And we also see that for a fixed value of mu, for example, right here, then as we increase the sample size from 9 to 25 to 36 to 64 and then up to 100, we see that the probability of rejecting increases. In other words, the power is increasing. Here we have the power curves for a left-tailed z-test of a population mean for 5 different sample sizes. The null hypothesis is true if mu is equal to mu sub 0 or to the right of that. All right, and if mu is to the left of mu sub 0, then the alternative hypothesis is true. Now, we can see again that all 3 of these curves go through the point mu sub 0 and 0.05. And again, the reason is because these tests are done at a 5% significance level. Now, for values of mu to the left of mu naught, but not too far away from mu naught, again, we don't have too much power for detecting that difference. We don't have too much power for detecting that the null hypothesis is not true. But for values of mu that are further away from mu naught, we see that the power does increase. And also for a given value of mu in the alternative hypothesis space, let's say right there, then we see that as we increase the sample size, the power increases as well. So as we get more information from the population, we are better able to see that the alternative hypothesis is true for any given value of mu naught in the alternative hypothesis space. And so then we have power curves for a right-tailed z-test of a population mean. And so for values of mu that are at or to the left of mu sub 0, the null hypothesis is true. If mu is greater or to the right of mu sub 0, then the alternative hypothesis is true. Again, note that these 5 curves all go through the point mu sub 0 and 0.05. That's because each of these, for each of the 5 sample sizes, we're looking at the power curve with a significance level of 0.05. We see that as for values of mu that are to the right of mu sub 0, so therefore for which the alternative hypothesis is true. But if mu is not too far from mu sub 0, we see that we're again not going to have much power for detecting the fact or discerning the fact that the alternative hypothesis is true. But for values of mu that are further and further away from mu sub 0, we see that we have more and more power. Regardless of the sample size, as mu increases, as it gets further and further away from the null hypothesis space, we see that we have more and more power for detecting that fact. And then finally, for a given value of mu, let's say right here, we see that as we increase the sample size from 9 up to 25 to 36 and so forth, we see that the power increases as well. So with these graphs of the power functions, we've seen that as the true value of mu gets further and further away from the boundary of the null hypothesis space into the alternative hypothesis space, we see that we have more and more power for detecting that the null hypothesis is not true. But as mu gets closer and closer to that boundary, all right, then it becomes more difficult for the test to see that the null hypothesis is not true, and so we have less and less power. And the other thing that we've seen is that for a given value of mu in the alternative hypothesis space, as we increase the sample size, we get more and more power. The tests become better and better able to detect that the alternative hypothesis, that the null hypothesis is false and that the alternative hypothesis is true. And again, that's because as we increase the sample size, we're getting more and more information about the population. All right, so these are the characteristics that we need to be concerned about, we need to think about when designing experiments. Whenever we are performing experimentation, or a researcher is, and perhaps you're a statistician and you're helping a researcher to plan a study, we need to make sure that we are utilizing all of the resources that are being expended in the experimentation process, the money, the time, the experimental material, that we are using it in the best way we can, in the most efficient and effective way we can, because the researchers want to get the most bang for their buck. They want to get the most information they can from the experimental material and other resources that they are expending and in fact investing in the experimentation process. So it would be very wasteful if we were designing an experiment or performing an experiment in a way that is not as efficient and effective as possible. So while one of the primary purposes of considering experimental design and learning about experimental design techniques, one of the primary purposes is to make sure that we can identify the experimental design used in an experiment so that we can determine the appropriate method of analysis so that we have a valid analysis. The other very, very important aspect of experimental design which is a prospective consideration, right? We're considering it before we ever even start the experimentation process. But we want to make sure that we are designing an experiment in such a way that we will have as much power as possible and as much precision as possible obtained from the experiment using the experimental material and all the other resources that go into that.